Assuming you went through that dark opening, you would arrive at a greater universe. There is currently an association between quantum processing and dark openings. In this educational video, we explore a noteworthy and frightening disclosure made by the James Webb Space Telescope inside a dark opening, as explained by none other than Bill Nye. The science guy is a star so large that even light cannot escape from it due to its incredible gravity. The secrets of dark openings have baffled researchers for decades. However, recently, thanks to extraordinary technological capabilities, we have witnessed something truly surprising. A very massive dark opening consumes the equivalent of one Earth per day. The most compelling discovery is the very first picture of a dark opening in space. Prepare yourself as we dive into the profound details of this astonishing revelation and what it might mean for how we interpret the universe. Stars toward the end of their lives, much larger than the sun, run out of fuel and begin to collapse under their own gravity. Dark openings are fascinating to understand. It was truly a challenge to locate the first one, even though Einstein's theory of relativity predicted their existence. Much like stars, dark openings don't emit any light. Instead, their size and spin are the only measurable properties. While visual evidence of dark openings is now spreading, definitive confirmation was missing for a long time. The first dark opening, Cygnus X1, was observed in 1964. But it took more than 30 years for experts like Stephen Hawking and Kip Thorne to agree on whether Cygnus X1 was indeed a dark opening. Hawking, a significant figure in black hole research, was convinced of their existence, but cautious due to the lack of conclusive discoveries. By 1975, Hawking and Thorne were nearly 100% sure that Cygnus X1 was a black hole. And by 1988, their confidence reached 95%. Still, they waited until 1990 to fully endorse the evidence when further observations provided adequate confirmation. The initial discovery of Cygnus X1 was made using 2 Geiger counters launched on a suborbital rocket. They detected a signal pinpointed to a system 7,200 light-years away. This system featured a bright blue giant star orbiting another massive object emitting strong XORs. Consistent with a dark opening, much research has focused on Cygnus 10-1 since its discovery. It has been revealed to be 21 times the mass of the Sun, making it the largest stellar mass black hole observed without the use of gravitational waves. This revelation challenges long-held assumptions about black hole formation and the mass loss experienced by stars over their lifetimes. Cygnus X1 breaks records in several ways, not only with its incredible mass, but also with the fastest rotation speed of any black hole observed to date, nearing the speed of light. These findings defy the standard model of black hole formation, although definitive evidence of dark openings has only recently been found. It is increasingly clear that they are scattered throughout the universe, even if researchers eventually unravel all the mysteries of Cygnus X1. The first of its kind, countless others still hold many secrets. Less than 2,000 light-years from Earth, researchers have discovered a dormant beast, the Milky Way's largest known stellar mass black hole, Gaia BH3, with a mass several times greater than our Sun. Gaia BH3 is the second closest known black hole to Earth. Despite this, it remained undetected until now. Gaia BH3 was discovered accidentally while researchers from the European Space Agency examined data from the Gaia mission, which maps our galaxy in 3D. This dormant black hole, not actively siphoning energy or matter from a companion star, came as a complete surprise. Typically, stellar mass black holes in the Milky Way have masses several times that of the Sun. Cygnus X1 holds the record at 21 solar masses, but Gaia BH3, at 33 solar masses, still pales in comparison to the supermassive black holes, for example, Sagittarius A** in our galaxy, which is 4 million times more massive than the Sun. Gaia BH3 is the second closest black hole to Earth, behind only Gaia BH1, which is 1,500 light-years away, and twice the mass of the Sun. COSMOLOGIST now have more evidence to determine how stellar mass black holes form. These black holes, which form at the end of massive stars' lives, are believed to originate from stars with lower concentrations of heavy metals. These metal-poor stars, mostly composed of hydrogen and helium, are thought to experience slower mass loss, leaving more material behind to form large black holes when they die. Using the James Webb Space Telescope, JWST, scientists have detected a very massive red black hole in the early universe. As the universe expanded, this supermassive black hole took on a reddish hue. 700 million years after the Big Bang, light traveling toward us became redshifted, suggesting a thick layer of gas and dust surrounding the black hole. Lucas P. Final and Iobi of the Bengal University of the NAS Cosmology Group calculated the black hole's mass using JWST data, estimating it to be around 40 million solar masses. This revelation stands out in the early universe, showing that this enormous black hole is rapidly consuming surrounding gas and dust, located about 12.9 billion light-years from Earth. This quasar was first identified by its red appearance. Quasars are formed when massive amounts of material surround extremely large black holes, forming a disk of gas and dust that feeds the black hole. The intense gravitational influence of the black hole heats the matter, causing it to shine. Light emitted by quasars can be so bright that it outshines all the stars in their host galaxies. The JWST identified this very large black hole as a small point of intense radiation, initially mistaken for a peculiar star-forming galaxy. Color analysis later supported the theory that it was indeed a supermassive black hole. Its small size and massive nature set it apart from other quasars. In the early universe, this discovery was made possible through gravitational lensing, a phenomenon predicted by Einstein in 1915. His general theory of relativity proposes that objects with mass warp the fabric of space-time, creating curvature that causes gravity. The more massive the object, the more extreme the curvature. This curvature also affects light emitted by stars, bending it as it passes near massive objects. Gravitational lensing allows us to see distant objects that would otherwise be invisible. JWST used this effect, aided by a galaxy cluster called SMXJ7233, to magnify distant galaxies and reveal the red quasar. This new data adds to the growing body of evidence that the early universe was populated with very large black holes, possibly millions or even billions of times more massive than the Sun. Now that this phenomenon has been discovered in several early universe supermassive black holes, it sheds light on the development of both black holes and the host galaxies, as well as the relationship between the two. The classic chicken or the egg problem at a galactic scale remains unresolved. Did the galaxy or the black hole come first? How massive were the first black holes, and how did they evolve? Researchers may also have discovered evidence that microquasars, black holes consuming matter from energy-rich stars, are cosmic particle accelerators, releasing high-energy astronomical beams that reach Earth. These massive black holes feed on matter from nearby supergiant stars in Maie and binary systems. Some of the stellar matter is expelled as relativistic jets traveling at incredible speeds. Microquasars are smaller versions of quasars, each fueled by supermassive black holes consuming surrounding matter. In 1912, high-energy particles were detected hitting Earth with energies reaching 10 electron volts, vastly more energetic than anything produced in the world's most powerful particle accelerator, the Large Hadron Collider. This suggests that supermassive black holes and microquasars are the universe's most powerful particle accelerators. However, evidence of microquasars accelerating particles to such high energies has been scarce until now, using the high-energy stereoscopic system, HESS. Researchers identified highly energetic gamma rays from the jets of the most powerful microquasar in the Milky Way, establishing a link between cosmic rays and microquasars. The microquasar SS433 produces high-energy gamma rays through jets that interact with surrounding matter, creating a shock front that accelerates electrons to extreme velocities. These gamma rays are the result of that interaction. SS433 was the first microquasar ever discovered. Located at the center of the W50 supernova remnant, affectionately nicknamed the Manatee Nebula, SS433 has been the subject of extensive study for decades. The system consists of a white supergiant star and a darkish establishing approximately 10 to 20 times the Sun's mass. They orbit each other every 13 Earth days, with the star's outer layers being stripped through the darkish opening's gravity. A number of this material forms an accretion disk around the darkish opening, while other parts are ejected as jets touring at 26% of the speed of light. These jets spiral in a wobbly pattern, shaping the W50 supernova remnant and giving it the appearance of a cosmic manatee. The jets fade over time but reappear as a phenomenon driven by the recurring nature of SS433's activity. The jets from the darkish opening also interact with the surrounding matter, developing a complex interaction between the dark opening and its surroundings. This behavior makes SS433 one of the most fascinating and enlightening objects in the study of microquasars and their role in cosmic particle acceleration. In spite of SS433 being the first recognized microquasar, much remains unknown about how dark openings accelerate particles to such extreme energies and their broader impact on the universe. Researchers use various techniques, such as indirect measurements, to understand these cosmic phenomena. For example, dark openings can be discovered through their interactions with neighboring stars and matter, as evidenced by the dramatic boom in X-ray emissions as material is pulled into there. Gravitational grasp. This phenomenon is critical in understanding dark openings and their influence on the universe, providing crucial insights into the evolution and behavior of these enigmatic objects. Within the realm of dark opening research, the recent discovery of the most distant known dark opening and unparalleled 13.1 billion light-years away has further expanded our understanding of these cosmic giants. This discovery, made possible by the capabilities of the James Webb Space Telescope, JWST, reveals a very massive dark opening formed less than 1 billion years after the Big Bang. This early formation challenges existing theories about dark opening development and galaxy formation. Observations suggest that these early dark openings may have played a major role in shaping the structure of the universe by influencing the formation and development of the earliest galaxies. In addition to their role in galaxy formation, dark openings have been linked to powerful cosmic phenomena known as active galactic nuclei, AGN. AGNs are characterized by extremely luminous emissions from the regions around supermassive dark openings at the centers of galaxies. This emission occurs when material from the surrounding accretion disk is heated to extreme temperatures as it spirals inward, emitting X-rays and other forms of radiation. Studying AGNs provides valuable insights into the feeding behavior of dark openings and their effect on their host galaxies. These studies have shown that AGNs can significantly influence galaxy evolution by regulating star formation and dispersing heavy elements throughout the galaxy. Recent advancements in gravitational wave astronomy have provided a new way to probe the properties of dark openings. The detection of gravitational waves from merging dark openings by observatories, such as LIGO Laser Interferometer Gravitational Wave Observatory, and Virgo, has opened a new frontier in understanding these elusive objects. Gravitational wave ripples in spacetime caused by accelerating massive objects allowed researchers to measure the mass, spin, and other properties of dark openings that are otherwise difficult to study. These observations have confirmed the existence of dark openings with masses ranging from a few to several solar masses. including the detection of dark opening mergers resulting in the formation of even more massive dark openings. Another intriguing aspect of dark opening research involves their role in the production of high-energy cosmic rays. Cosmic rays, highly energetic particles traveling through space, are thought to be accelerated by dark openings, especially those in active galactic nuclei or microquasars. The process involves the interaction of relativistic jets produced by dark openings with surrounding matter, creating shockwaves that accelerate particles to near-light speeds. Understanding the origins of these cosmic rays is vital for interpreting their impact on the interstellar medium and the broader cosmic environment. In addition to their influence on cosmic rays, dark openings are also associated with the formation of complex structures called relativistic outflows. These outflows are powerful jets of matter ejected from the regions around dark openings, traveling at nearly the speed of light. The study of these outflows helps researchers understand the mechanisms behind the formation and evolution of supermassive dark openings and their impact on their host galaxies. Observations of these jets have provided vital information about the magnetic fields and particle acceleration processes occurring in the vicinity of dark openings. Theoretical work has also explored the nature of primordial dark openings, which are believed to have formed in the early universe shortly after the Big Bang. Unlike stellar mass or supermassive dark openings, primordial dark openings would have formed from density fluctuations in the early universe rather than from collapsing stars. If they exist, primordial dark openings could account for some of the dark matter in the universe. Identifying these elusive objects remains a significant challenge, but their study could offer new insights into the fundamental properties of dark matter and the early universe. Furthermore, dark opening thermodynamics and the study of Hawking radiation remain areas of active research, proposed by Stephen Hawking. This theoretical radiation suggests that dark openings should emit particles and slowly lose mass over time. While direct detection of Hawking radiation is currently beyond our technological capabilities, it has major implications for our understanding of dark opening operation and the ultimate fate of these objects. Theoretical models and simulations are helping to explore how this process could affect the lifespan and properties of dark openings. Another fascinating development in dark opening research is the investigation of the dark opening information paradox, a long-standing puzzle in theoretical physics. This paradox concerns whether information that falls into a dark opening is lost forever or if it can be recovered in some form. Recent advances in quantum information theory and holography have led to new insights into this issue, suggesting that information may be preserved in a highly scrambled form and potentially recoverable in some way. Eventually, the detection of gravitational waves from dark opening mergers has not only confirmed the existence of these cosmic giants, but also provided a unique way to study their formation and evolution. These waves carry information about the masses, spins, and dynamics of the involved dark openings, offering a new method for probing the fundamental properties of these mysterious objects. Ongoing observation and analysis of gravitational waves will undoubtedly reveal much more about the nature of dark openings and their role in the universe. In summary, dark opening research continues to evolve with advancements in observational optics techniques, theoretical models, and new discoveries from the distant massive dark openings in the early universe to the complex interactions of microquasars. The study of dark openings remains a dynamic and fascinating field with profound implications for our understanding of the cosmos.